So let's start with the most important question right away. What exactly is Docker? Well, Docker, in the end, is a container technology. It's a tool for creating and managing containers. Okay, so that clearly is a nice sentence, but what exactly does it mean? What's a container in software development, and why might we want to use it? Well, a container in software development is a standardized unit of software, which basically means it's a package of code and that's important, the dependencies and tools required to run that code. So for example, if you're building a Node.js application, Node.js is a JavaScript runtime which could be used to execute JavaScript code on a server. If you had such an application with a container built with Docker, you could have your application source code in that container, as well as the Node.js runtime and any other tools that might be needed to run that code. And the advantage is that the same container with the same Node.js code and the same Node.js tool, so the same Node.js runtime with always the same version, will always, and that's the key thing, will always give you the exact same behavior and result. There are no surprises because it's all baked into the container. It's always the same. But maybe it's even easier to understand this concept if we take a step back. Think about a picnic basket. A picnic basket contains everything you need to have, well, a picnic, dinner in the park, something like this. It contains the food and it contains the dishes which you need. And therefore, you can take that basket and take it everywhere where you want to have that picnic and you're ready to go. You have it all in that basket. You can also share that basket with a friend and that friend can have that same picnic you would have had otherwise. There are no surprises. You have the dishes and the food. You don't have to look for dishes at the place where you want to eat. And maybe then you have soup with you. Might be strange with a picnic, but whatever. And then you don't have the dishes for eating soup. If you pack your own picnic basket, it's all in there. And that's the idea behind a picnic basket. It's the same idea behind containers and Docker, which is just a tool for creating and managing these containers. Now, the term container might be strange at first, because if you hear about a container, you might think about something like this. At least that is what I know as a container. But actually, it's not a bad comparison. This is a container we would load onto ships or trucks to move goods around. Well, and it's the same idea as with Docker containers still. We have standardized containers here like this, and we can fit various goods into these containers. But they are then self-contained and isolated. The goods in one container don't get mixed with goods from another container. If you need something like cooling, it can be built into the container, and therefore the container works standalone. And it can be put onto any ship or any truck which is able to handle containers. And that's exactly the same with Docker containers. We have our units of software, our packages with code and with the dependencies to run this code, and we can then take it anywhere where Docker runs. And we will then be able to run exactly the same application with the same environment wherever that is. We don't need to worry about installing any extra tools in that place where we want to run our application because it's all in the container. That is what containers are, and that is what Docker is about, because Docker is just the tool for building these containers. Now, the good thing is that support for containers is built into modern operating systems, or at least there it's easy to get started with them, and Docker can be installed on all modern operating systems to then work with it there. And Docker then in the end is a tool that simplifies the creation and management process of these containers. You wouldn't need it to create containers, but it's the de facto standard for doing that since it makes that task so super simple. So we now know what containers are and that Docker helps us create these containers. I also already outlined some advantages, but still you might wonder, why exactly do we need containers in software development? Maybe the example made sense for a picnic basket, And to some extent, it makes sense for a software development, but is it really that important and useful? Yes, it is. We should just ask ourselves one simple question. Why would we want independent, standardized application packages in software development? Well, for one very good and typical example, and one of the main use cases of Docker, I would say, we of course often have different development and production environments. And here's a simple example. Let's say you created a Node.js application and you wrote some code there which requires Node.js version 14.3 to run successfully. And this is not some made-up example. The example you see here is Node.js code which uses a feature called top-level await. Now, you don't need to know Node.js to follow along with this course. For the moment, it's enough to know that this is a feature which would not work in older versions of Node.js. We need Node.js 14.3 or higher to execute this code successfully. The problem is that we might have that version installed on our local environment, on our development environment, on our local machine. But if we then take this application and we deploy it onto some remote machine, onto a server where it should be hosted so that the entire world can reach it, then on that remote machine, we might have an older version of Node.js installed, maybe 14.1 or 12 or 8, whatever. And all of a sudden, the code which worked locally on our machine doesn't work there anymore. And depending on what's going wrong, it can take quite some time to figure out what the problem was. So having the same, and with that I really mean the exact same, development environment as we have it in production can be worth a lot. And that is something where Docker and containers can help you. You can lock a specific node version into your Docker container and therefore ensure that your code is always executed with that exact version. And all of a sudden, that potential problem is gone and can't occur anymore because your application runs in that container, which brings its own Node.js version. So that's one example. Kind of related to that would be another example: different development environments within a team or company. Let's say we're in a big team. I'm working there and you are working there. And now we're working on the same project. For example, that same Node.js application again. Now, because you haven't worked with Node for some time, or because you didn't need to update, you still have an older version of Node.js installed on your system. And I have the latest version. So I wrote this code with top-level await, and when I share the code with you, it doesn't work for you. Now, obviously, you might say, updating Node.js is no problem. I can easily update it on my system and we're on the same page again. Yes, but for one, it's just one example. There could be more complex projects with more complex dependencies which you need to manage and install. And in addition, even in that one example, it's still annoying that we're not able to work on the same code base together and we have some guarantee that it will always work and that we always use the same environment. We want that reproducibility in software development, and therefore even here, if we're not deploying it at the moment, having that locked in environment with everything the code needs in the container can be worth a lot. And now last but not least, even if you're working on your own, then still Docker and containers could be very useful. Because if you have multiple projects on which you're working, then you might have clashing versions. Let's say one project uses Python version 2 still for whatever reason, another project uses the latest version of Python. The same maybe with Node.js or PHP or whatever kinds of projects. There you would have clashing versions, and that means that whenever you switch from project A to project B, you have to uninstall the wrong version and install the right version. For example, if one project needs Node version 12, the other project needs Node version 14. If you switch projects, you have to uninstall version 14, install version 12 instead, and vice versa. So switching between projects becomes a big hassle and is no fun at all. And that again is something where Docker and containers can help us. We lock our versions into the containers, and every project has its own container. And therefore, if we then switch projects, it'll just work like that. We don't need to uninstall and reinstall anything because it's all in the container, not globally on our host machine. And therefore, switching projects becomes as easy as launching a different container. And these are all things we're going to see throughout this course, and you're going to learn everything you need to solve these problems throughout the course. And that's why we might want to consider working with containers and why Docker is a quite helpful tool. So now we know what Docker is and what containers are and why we might want to use it. We will learn what exactly Kubernetes is a little bit later in the course, by the way. But let's stick at the basics for now, containers and Docker. The problems solved by Docker and containers make sense, hopefully, and it makes sense that we might be looking for a solution like Docker and containers. But if you've been in the software development area for some time, you might also think to yourselves, why Docker and why containers? Isn't that a problem? So that reproducible environment thing, isn't that a problem which we can solve with virtual machines? So machines running on our machines, virtual machines with virtual operating systems encapsulated in their own shell, independent from our host operating system. Isn't that a solution? Well, kind of. With virtual machines, we have our host operating system, Windows or Mac OS or Linux. And then on top of that, we install the virtual machine. So a computer inside of our computer, so to say. This virtual machine has its own operating system, the virtual operating system which runs inside of that virtual machine. Let's say Linux. Then in this virtual machine, since it is like a computer, it's just virtually emulated, you could say, but inside of that virtual machine, we can then install extra tools. We can install whatever we want in there because it is just another machine, even though it just exists virtually. But we can install all the libraries, dependencies, and tools which we need, and then also move our source code there. And hence, since it's an encapsulated virtual machine with everything our program needs and all the tools being installed there, we kind of have the same result as with Docker and containers. We have an encapsulated environment where everything is locked in. And we could then have multiple such environments for different projects, or we could share our virtual machine configuration with a colleague to ensure that we're working in the same environment. Well, this works, but there are a couple of problems. One of the biggest problems is the virtual operating system and in general the overhead we have with multiple virtual machines. Every virtual machine is really like a standalone computer, a standalone machine running on top of our machine. And therefore, if we have multiple such machines especially, we have a lot of wasted space and resources. Because every time a brand new computer has to be set up inside of our machine, and that of course eats up memory, CPU, and of course also space on our hard drive. And that really can become a problem if you have more and more virtual machines on your system. Because you have a lot of things which are always the same and still duplicated, especially the operating system. You might be using Linux in all your virtual machines and still it's installed separately in every machine. And that of course wastes a lot of space. In addition, you might have a lot of other tools installed in every virtual machine which your application doesn't need directly, but which still are set up as a default. And that can be a problem. So to sum it up, virtual machines have a couple of pros and cons. They do allow us to create separated environments, and we can have environment-specific configurations in them, and we can share and reproduce everything reliably, but we do have this redundant duplication, that wasted space. Performance can be bad since we have an extra machine running on top of our host system, and especially if we have multiple such machines, performance can really degrade. And in addition, even though it is reproducible and shareable, that also can be tricky because you still have to set up that virtual machine on every system where you want it, and you have to then configure it in exactly the same way. There is no single config file you can necessarily share. If you want to deploy your application, so from development to production, you also have to ensure that you configure your production machine in the same way as your virtual machine. Alternatively, you run your virtual machine on your production machine, but that wasted performance, that's something you might not want to do in production. So it solves the problem, but not in a perfect way. And you might guess that's why we have Docker and containers. And actually, it's really important to understand that containers is the key concept here. Docker is just the de facto standard tool for creating and managing them. So why does Docker help us with that? How do containers solve that problem in a better way than virtual machines do? With containers, we still have our host operating system, Windows, Mac OS, Linux, whatever it is, but then we don't install a couple of machines in the machine. Instead, we utilize built-in container support, which our operating system has, or emulated container support, something Docker will take care about that this works. And then we run a tool called the Docker engine on top of that. And that will all be set up by Docker when we install it, by the way. And then, based on that Docker engine, which now runs on our system, which is just one tool, one lightweight small tool being installed there, we can spin up containers. And these containers contain our code and the crucial tools and runtimes our code needs, like Node.js, for example, but they don't contain a bloated operating system, tons of extra tools, or anything like that. They might have a small operating system layer inside of the container, but even that will be a very lightweight version of an operating system, much smaller than anything you would install in a virtual machine. And you're going to see how containers work exactly and how you create them throughout this course, of course. Now, the other great thing about containers is that you can configure and describe them with a configuration file, and you can then share that file with others so that they can recreate the container, or you can also build the container into something which is called an image, which you need to do anyways, and then you can share that image with others to ensure that everyone's able to launch that same container which you have on your system on their systems. And obviously, we're going to dive in detail into images and containers throughout this course. So you are going to learn all about that step by step. So if we compare containers to virtual machines, we have a couple of advantages on the container side. They have a low impact on our operating system and machine, they're very fast, and they use minimal disk space. Sharing, rebuilding, and distributing them is very, very easy because we have these images and these configuration files. And we still have encapsulated apps and environments with everything our app needs, but nothing more, which is perfect, which is exactly what we want. Virtual machines, on the other hand, have that bigger impact on the operating system. They tend to be slower, and they also tend to eat up more of our disk space. In addition, as I said, sharing, rebuilding, and distribution, that all can be done, but also may be trickier than with containers and Dockers. Still, of course, we encapsulate our environments, but we don't just encapsulate our app and what it needs to run, but entire computers. It's like having a totally separate machine, which in rare examples or in rare use cases could be an advantage, but often it's just a bloated thing which you don't necessarily need. So by now we have a first good idea of what Docker is, what containers are, and why it might be interesting to work with these things. Now, of course, to work with Docker, we need to install it. So in order to create these containers and work with them, we need to install Docker. And when it comes to installing Docker, the exact steps depend on the operating system you're using and then also on certain system requirements which you need to meet. And for that, it's best if you visit docker.com. There, if you go to Developers, Docs, and then to download and install, you can choose your operating system and you will find the system requirements there. And for example, you see for Mac, you need a hardware newer than 2010, and a Mac OS version which is 10.14 or newer, at least at the point of time I'm recording this. For Windows, you also got certain requirements. For example, you need Windows 10, Pro, Enterprise, Education, or Home. And for Linux, you actually don't have any specific requirements because there you'll be able to use Docker basically everywhere. Now I will come back to the different platforms and the exact installation steps in a second. But for the moment, you should just check whether you meet these requirements or not. For macOS, if the requirements are met, you can install a tool named Docker Desktop, which is the recommended tool you should use when working with Docker. If the requirements are not met, then you can install an alternative tool called Docker Toolbox. Docker Desktop is the recommended tool, but if there is no way of getting that to run, use Docker Toolbox instead. I will show you both, by the way. I will show you the setup steps for both tools over the next lectures. For Windows, it's the same. If the requirements are not met, you should install Docker Toolbox. If they are met, you should use Docker Desktop, just as on macOS. And for Linux, it'll be a bit easier. There you have no Docker Toolbox or Docker Desktop tool. Instead, Linux natively supports the Docker engine, and therefore you can directly install that engine on Linux. Docker Toolbox and Docker Desktop are basically just tools that bring Docker to life on non-Linux operating systems, you could say, because the Linux operating system natively supports containers and the technology Docker uses, you could say. So therefore, for Linux, if you want to install Docker, you can use the attached resources, which in the end also just guide you through some setup steps for Linux, where you install Docker just like this on Linux. It'll be really straightforward, and once you're done with that, you will be able to run the Docker command. Now for macOS and Windows, as I mentioned and explained, you can't install Docker just like that. Instead, you need the recommended Docker Desktop tool, or, if not supported, the older Docker Toolbox tool. And now over the next lectures, I will show you installation on both macOS and Windows, and I will show both Docker Desktop and Docker Toolbox. We start with macOS in the next lecture, Windows thereafter, and thereafter Docker Toolbox for both operating systems. Therefore, choose the lecture which makes sense for you, so which matches your operating system and your answer to the question whether you meet the requirements I showed you a couple of minutes ago or not. And thereafter, we'll all have the same setup where you can use Docker. So no matter how you install it, in the end you will be able to use Docker. And in this course I will use macOS for my videos, but what I show you there and what I teach you there applies in the same way on Windows. You will execute the exact same commands on Windows. So with that, let's dive into the different installation steps in the next course lecture. Now in this lecture we're going to install Docker for macOS. And therefore, on this Get Started page on docker.com, here under Docker Desktop, we're going to download the version for Mac. It should automatically pre-select the right one. If it didn't, you can simply switch to it. So click this and download this to some folder of your choice. This is just the installer basically, so it's really up to you where you want to store it. And I will be back once this download finished to then show you the very complicated installation process, and to then also show you how to finish up the installation and what's important to keep in mind when it comes to working with Docker. So, download finished. Now we can execute this file here on macOS. and let it open the Docker DMG file. And now the installation really is just that you drag this Docker app, which for you might have a real Docker icon and not this placeholder, which for whatever reason I have here, and drag it to the applications folder. That really is all. This will now copy over Docker. And once this is done, you can close this and simply run Docker. You will now have this Docker app available as an application you can run. So I'm running it here. And you now see this whale here in the status bar on the top. Now here, you can go to Preferences to bring up this graphical user interface here. And there you can set up some general things. You can, for example, control whether Docker Desktop should start when your Mac starts. You can set up automatic updating. And you can also configure other things. Some of these things or settings are topics I'll come back to later in the course. For example, file sharing. Generally, you should be fine with all the defaults here. Only change things if you know what you're doing. Besides the startup thing here, which of course is up to you whether you want to have this changed or not. Now, one important note is that on the bottom left corner here, you will see that Docker is currently running. And it will start whenever you start Docker Desktop. So if you don't automatically start it with startup of your system, you should start it manually by running this Docker app before you try to run any Docker commands against it. Because all those commands which you'll see throughout the course, which we execute in the command line, will only work if Docker is running. So you should always make sure that you started Docker, for example, by starting the Docker Desktop app in order to run commands thereafter. Now with that, that's it for the moment. You can close this window. It's still running here as long as you have this icon here. And you can always shut Docker down with this menu here. But for the moment, I'll keep it up and running. And again, make sure it is up and running when you plan on working with it. And that's already it with the Docker for macOS setup. For older versions of macOS, check out this extra lecture, which comes after the next lecture. And for Windows, also check out that next lecture. And with that, you'll then be ready to dive into Docker and start writing some commands to learn how Docker really works and what you can do with it. Now in this lecture, we are going to install Docker on Windows. So obviously you can skip it if you're on macOS or Linux. Now we can click on Get Started to be taken to the page where we can download Docker Desktop for Windows. And we will use that, but before we start doing that, actually go to Developers and then Docs here in the menu. And then there click on Download and Install and then Docker Desktop for Windows, so that you can learn about these system requirements which you have to meet in order to be able to install it. And you need either Windows 10 Enterprise, Pro, or Education, or Windows 10 Home to use Docker Desktop. If you have an older version of Windows, Windows 8 or 7, the next lecture is for you, because there I show you an alternative way of installing Docker. But if you have any chance of using Docker Desktop, which we're going to install in this lecture, definitely use that chance. So if you, for example, are able to upgrade to Windows 10, you might want to consider doing that. Now, if you got Windows 10 Pro, Enterprise, or Education, you need to have Hyper-V and containers features enabled. And in order to enable both of that, you can search for Windows 10 Enable Hyper-V to find certain instructions on how to do that. You best follow the approach described here on the official Microsoft web pages. And in the end, you just need to run one command to enable Hyper-V. You need to do that in PowerShell, which is a default tool that ships with your Windows installation, which you have to run as administrator. Now, once you are running this as administrator, make sure you copy and paste this command into PowerShell and simply execute it. And this will enable a functionality in your operating system, which Docker Desktop needs to, in the end, run these Docker containers on your system. So make sure you enable this, and thereafter, in the same administrator started PowerShell session, run another command which you find in an attached file. Actually, in that attached file, you find both commands, but now we need this enable containers command here. And run this in your PowerShell as well. With that, you enable the two features which you need to enable. If you are on Windows 10 Home, then you got a separate page here with more steps you need to follow in order to install Docker Desktop. So click on that Install Docker Desktop on Windows Home link then, and make sure you meet all these requirements here. Specifically, you need to enable the WSL2 feature on Windows. And you got another link to the Microsoft documentation, which informs you how you can do that. It's again, in the end, very simple. You first of all need to enable the WSL feature by running this command, again in PowerShell, started as an administrator. You don't need to do this on Windows 10 Pro, but you need to do this on Windows 10 Home. And then execute this command here in PowerShell. And once you did that, you need to update to WSL2 by following the steps outlined here. Thereafter, make sure you enable the virtual machine feature by running this command here in PowerShell as administrator. Obviously, you can also leave PowerShell up and running. So hit enter. And now with that, you need to download a Linux kernel update package, because WSL2 in the end is a Linux installation inside of your Windows installation. And that Linux installation will be used by Docker Desktop and by Docker itself then. Now therefore, we now needed to enable and update it. Now we need to download the Linux kernel update package, and that again can be done with the link you find here. It simply downloads a file which you can execute, walk through that installer, which should be super quick, and which in the end then just updates your Linux kernel inside of that Linux system, which you have inside of your Windows system. Then execute this command here in PowerShell as administrator to set version 2 of this Linux inside Windows solution here as a default version. And then install an actual Linux distribution of your choice. So that will then be the Linux operating system running inside of your Windows system, in addition to Windows, of course. It does not replace Windows, it just runs in addition. Now, here you can really follow these instructions and pick any distribution you want. Ubuntu is a very typical choice here. And simply then walk through the installer here and follow the other steps which are outlined in this article. You don't need to install the Windows terminal here. If you don't want to, you can, but you don't have to. And you're therefore done. Now, if you're facing any problems, also have a look at the troubleshooting guidelines here at the bottom of this Microsoft article, which you of course also find attached to this lecture. And once you did all of that, you're also prepared to install Docker Desktop on your Windows 10 Home installation. Again, this was not required, as I mentioned before, if you are on Windows 10 Pro or Enterprise or Education. Of course, you also must meet the hardware requirements outlined here and outlined here, which are the same requirements. And once all of that is set up, therefore, you now can use that installer, which you find on the Getting Started page. So simply download Docker Desktop for Windows, and then wait for this installer to be downloaded, which can take a while, of course. And once it is downloaded, walk through the installer. Now we're going to do this together, so let me just wait until this is finished and I'll be back thereafter. Now once this was downloaded, simply double-click on the downloaded executable to start the installer. You might be prompted to enable WSL2 Windows features, especially on Windows 10 Home, and you should then check this. If you don't have this option, you can also proceed without it though. If you're prompted to enable Hyper-V, then check this. So long story short, whichever checkboxes you see here, just tick them. Of course, with the exception of the Add Shortcut to Desktop checkbox, that is up to you, whether you want to do that. Then click OK, and this will now install Docker Desktop and therefore the Docker tool on your system. Now this again can take a while, so let's wait for this installation to finish. And eventually this should be done. Now once this is done, you might be prompted to restart your system. If you are, of course do so. And thereafter, after your system restarted, Docker might have started up automatically. Otherwise, simply execute Docker Desktop, this tool which we just installed. Make sure you execute and start it. And once you do start it, you should see this prompt here or this screen here. You also should have that whale in your system tray here, which proves that Docker is up and running. Here you can also always dive into the settings of Docker if you need to configure something, though for the most part you shouldn't need to do too much here. However, you should ensure that Docker is always up and running if you plan on working with it. So if there is no whale down there, you will not be able to execute Docker commands. So throughout this course, ensure that Docker is up and running if you want to work with it. Here in this graphical user interface, you can click on this gear icon to be taken to the settings, and here you can control whether Docker Desktop should start up when your system starts or not. For convenience, you might want to leave this turned on, but it's of course up to you. You also might have the option to choose whether WSL2 should be used. On Windows 10 Home, you should do that. On Windows 10 Pro, you can do it. As you see, it provides a better performance, but you can also use just this Hyper-V tool, which we enabled. Now, you don't need to do too much about the other settings you see here. You can ignore them for now. I will come back to them if we should need them throughout this course. And with that, we got Docker installed and we're ready to use it. You can now open up your regular command prompt. You don't need to run it as administrator. And there you should be able to enter Docker like this. And you should not get an error, but instead a list of commands you could use. And that proves that it works and that Docker was installed. Now we're soon going to use it for a more useful command than just this dummy command, but that's now the setup we need. Now, Docker Desktop is the recommended way of running Docker on macOS and Windows, but it's not available on every system. If you go to the developer docs part here on the Docker page, so if you visit docs.docker.com, you can click on Download and Install, and there you see the requirements for using Docker Desktop, both for Windows as well as for Mac. Now, the good thing is, for macOS, most systems support Docker Desktop. If you have Mac hardware newer than 2010 and you fulfill all these requirements, you will be fine. For Docker Desktop for Windows, you need Windows 10 essentially, as you saw in the last lecture as well. But if you don't fulfill these requirements, there is an alternative available for you. There is a tool named Docker Toolbox, which you can then use instead of Docker Desktop. If you Google for Docker Toolbox, you should find these toolbox installation instructions. It's a legacy tool because it's not recommended that you use it anymore, because it was replaced by Docker Desktop for Mac and Windows. Historically, Docker Toolbox was the only solution for all platforms. Nowadays, we have the more modern Docker Desktop solution. But for older systems, that's not available, so therefore there you need to stick to Docker Toolbox. Now, what is Docker Toolbox? The Docker tool runs natively on Linux. And to make it work on macOS or Windows, you in the end need a virtual machine. So a machine simulated on your machine, which holds a Linux installation in which Docker can run. Now, Docker Desktop for both Mac and Windows uses built-in operating system features for that, but older versions don't have these features. That's why you then need to install a virtual machine manually and install Docker inside of that machine. And that's in the end what Docker Toolbox helps you with. So, how do you use Docker Toolbox then? Well, first of all, you might want to verify that you really can't use Docker Desktop. But if you're at this point that you can't use it, you can follow the instructions on this page. And on this page, you, for example, can find out how to check whether your system supports the virtualization which is needed. For example, how to check it on Windows 8. If you don't fulfill the requirements listed here, you unfortunately can't use Docker on your system because you will not be able to install Docker Toolbox, and that is the last possible way of getting Docker to run. So make sure you check these requirements on Windows 8. For Windows 7, make sure you use a tool like Spacky or the hardware-assisted virtualization detection tool. And once you know that you are able to run a virtual machine, you can install Docker Toolbox. On macOS, by the way, check the Install Toolbox on Mac page here to find all the installation steps there. Though in general, these are the same steps as shown on Windows, so I will show it on Windows here, but this would be your macOS steps if you need to install Docker Toolbox on macOS because you can't use Docker Desktop. Now, how does this work? First of all, you need to go to the Toolbox Releases page and download the latest version there, and simply download the executable for Windows and the package file for macOS. So here I'll go with the executable for Windows, and this will now install everything you need to install to get Docker to run on your older Windows machine or on your older macOS machine. You find detailed installation instructions on that page we just visited, by the way, so definitely make sure you also check these steps here in case you should get stuck. So let's wait for this download to complete, and once it did complete, we can execute this installer which we downloaded. In that installer, simply walk through the different steps and pick a location where that should be installed on your system. Click Next. And then make sure you have all these things checked. Docker Toolbox needs VirtualBox, for example, which is a tool that creates a virtual machine on your system. And you should also ensure that all the other tools here are being installed. So click Next then. You can decide whether you want the desktop shortcut or not. You should definitely keep the second option checked though, that Docker binaries are added to your path. And you can in general go with the default settings here. So let's click Next and Install, and this will now install and set up all the tools Docker needs to bring up that virtual machine in which Docker then is able to run. Now eventually this will be installed, and you can then click Finish, and it should open up this folder with some shortcuts you can use to basically start Docker. You can simply click the Docker Quick Start terminal here, and this will open up a terminal in which you then can run the Docker command. Now you see, for me, I'm not able to start it because I have Hyper-V enabled on my machine, and therefore I should not use Docker Toolbox. But if you can't use Hyper-V, if you can't use Docker Desktop therefore, you should instead see something like this, and you will have an environment in which you can run Docker commands. So where you then, for example, can run Docker to see a list of all commands or execute all the different Docker commands you will see throughout this course. And that is it. This is then your environment in which you can work to run Docker commands and to work with containers as shown throughout the course. What you'll learn about Docker will be the same as if you used Docker Desktop. So the concepts are all the same. It's really just the environment in which you run Docker which is different. And as mentioned multiple times, if you got any chance of upgrading to Docker Desktop, definitely do that. It offers greater performance, doesn't clutter your system as much, and overall is the recommended environment for running Docker. So over the last lectures, we installed Docker. And I find it important to understand what exactly we installed there and what we do with these tools. In the end, we installed the Docker engine. We installed that no matter if you installed Docker Desktop, if you installed it directly on Linux, or if you used the Docker Toolbox. There, this Docker engine was simply set up in that virtual machine, which hosts Linux, which is simply required to run Docker. The virtual machine, by the way, just to make this clear, is really only there because your operating system doesn't natively support Docker. If it would, we wouldn't need the virtual machine, because the idea was to not use virtual machines. But even with that, it's just there to run Docker, and then your containers will run in that virtual machine. So we still will be working with containers. Anyways, we installed the Docker engine in the end. Docker Desktop installed it for us and made sure it works. Docker Toolbox installed it for us. And on Linux, we installed it just like that. Therefore, Docker Desktop, the tool which some of you at least installed over the last lectures, is really just a tool that made sure the Docker engine was installed and that it works. It includes a so-called daemon, a process which keeps on running and ensures that Docker works, so to say, the heart of Docker, and it contains a command line interface. And you also got that with Docker Toolbox and if you just installed Docker on Linux. The command line interface will play a crucial role because that is the tool we will use throughout this entire course to run commands, to create images and containers, and to work with Docker. So we got all of that installed by now. Throughout this course, you will also learn about a service called Docker Hub, which I want to mention right away. We're not using it right now. We also don't need to install anything for that, but that will be a service which will allow us to host our images in the cloud, in the web, so that we can easily share them with our systems or with our people. And we will also learn about a tool called Docker Compose later, in a standalone section labeled Docker Compose. This is a tool which kind of builds up on Docker, you could say, which makes managing more complex containers or multi-container projects easier. Last but not least, this course is also about Kubernetes, and therefore that's another tool, if you want to call it like this, we're going to explore later. It will also help us with managing complex containerized applications when we want to deploy them, but we will learn more about that when the time is ripe. So that's what we installed and some tools you should be aware of. And with that, let's now use the Docker tool we installed to get our hands dirty and create and run our first real container. Now in this course, we are primarily going to run a lot of commands in the command line, but we're also going to run these commands on projects which are written with Node.js or other programming languages. So there will be code in this course and there will be configuration files like this. Therefore, you will need a code editor to follow along. And you can of course use any editor of your choice, but I do recommend Visual Studio Code, especially if you don't know which editor to choose. It's a free editor, a free IDE, available for macOS, Windows, and Linux. It's amazing, and you can simply install it from code.visualstudio.com, walk through that installer, and then have that tool installed here, which you see in the background. You can then always open projects with File Open, and then opening the folder which contains your code. And if you want to have the same look as I do, you can go to the Preferences, and there on Color Theme, pick the Dark Plus Default Dark theme. That's the theme I'm using, which will give you that look. In addition, you can use the View menu here to adjust the appearance and show and hide side and status bars. And you can also go to the Extensions menu here to install certain extensions. And here I can recommend the Docker extension, since that will help you with writing these configuration files. It will actually make that a bit easier, so that's something you might want to look into. I can also recommend that you install the Prettier extension, because whilst you're not going to write a lot of code, this can help you with code auto formatting to basically automatically clean up your code. Besides that, that should be all, and these are also just some ideas, not something you have to use, just the setup I will be using throughout this course. And therefore, with that setup, let's now get our hands dirty and let's write some first Docker code or bring up our first Docker container. So let's create our first container and let's get our hands dirty, even though I will say right away that at this point, we're not going to understand everything here. We're just going to write some code and bring up a container, and we're going to understand all the details a little bit later in the next course section. I just want to immediately get something up and running. We also have this example to validate that everything is working as it should. So here's the example. You find it attached. It's a very simple Node.js application. And by the way, I just want to highlight, it's just an example. You don't need to know Node.js for this course. You can follow along even if you don't know it, because we're not going to write any Node.js code. You can use Docker for any programming language and any project and application written with any technologies of your choice. What you learn in this course will apply. It's just an example because I have to pick some programming language for the example in the end. So this is a Node.js application with some basic dummy code, and in the end this will start up a web server on port 3000, which will listen to GET requests on no particular path and will then send back some dummy HTML. I also got this dummy database connection code, which doesn't really connect, but just set a timer of 1 second until the server is launched in the end. And I'm having this here so that we have a top level await example, which is a Node.js feature for working with asynchronous code, which only works if you use Node.js version 14.3 or higher. So this is the Node.js code. If we would want to run it locally without Docker and without containers, we would have to visit nodejs.org and then download that latest version of Node.js, whichever version that is when you're watching this, walk through the installer that gives you, and then open up a new terminal and then run this app.mjs file by running node app.mjs. And actually, before we do that, we would have to run another command, npm install, which installs all dependencies listed here in package.json, which are simply third-party packages this app.mjs file needs to work correctly. Again, if that all doesn't tell you too much, that's no problem here. These are the steps we just would have to execute if we would want to run this code here locally on our machine. However, the idea with Docker was a different one. We want to run this code in a container. And for that, we first of all need to create a so-called image, because containers are always based on images, and you're going to learn more about that and this relation between image and container in the next course section. For the moment, to create such an image, we simply create a Docker file, so a file which is simply named Docker file without any extension. And in here, we now describe to Docker how our container in the end should be set up. And we do this by adding a couple of instructions. Now, since we are going to dive into images and containers in greater detail in the next section, I don't want to waste your time with a bunch of instructions which we don't fully understand yet. So instead, attached you find a finished Docker file, which in the end just has a couple of instructions that we want to use Node.js as a base image, so that we want to have Node.js available inside of our container, that we have a certain directory in the container file system. Every container has its own file system, so that we want to have a special directory in there in which we want to work, that we then copy the package.json file into our working directory. Then we run the npm install command to install all the dependencies our application needs. Then we copy the rest of the code here. Then we expose port 3000 to the outside world, because that's the port our application is listening on. And we want to be able to reach that port from outside the container, not just from inside the container. And then we execute app.mjs with the node command, which is available because we're running in a node environment. Again, this was the quick walkthrough. The details will follow in the next course section. Now, with that Docker file created, we open up a terminal. For example, here I'm using the terminal integrated into Visual Studio Code, the editor I'm using here. And with Docker set up, which we have at this point, we run docker build dot. And this builds the image, the Docker file, it finds in the directory in which you run this. Therefore, I'm using this integrated terminal here because this automatically launches in this project directory. So any commands I execute here run inside of this directory. So now this will build an image based on this Docker file, which is the first thing we need to do. So simply hit enter here. If you're getting an error at this point, make sure you got Docker installed and started. Start Docker Desktop if you installed that, and make sure Docker is running in the background. And therefore, at some point, this should then work. And what this now does is it grabs this node environment, which already exists. It downloads it from the cloud, from Docker Hub to be precise, but more on that later. And then it will set up an image for a container to be launched with all these setup steps being executed inside of the image. So it will give us an image which is prepared to be started as a container. So this now walks through all these steps, and after some time it should be done. You get a successfully built and then some ID for this image output. As a side note, on Windows your output looks slightly different. There you find the ID of the image which was built here. Now we can use this ID here and then run a container based on this image with the docker run command. Like this, docker run and then the image ID. However, actually, since our container here has a port to which we want to communicate, we actually need to publish that port on the container which we want to run. And we do this by adding the -p flag on Docker run here, and we then publish port 3000 on port 3000, which means we can use our local host on our local system to reach the application running on port 3000 inside of the container. Because by default, there is no connection between container and our host operating system. If we want to send HTTP requests, for example, to an application running in a container, we need to open up the port on the container to which we want to communicate. Otherwise, it's a locked network in the container and we can't reach it from outside. With that, however, we can hit enter, and this now will run this container. And you can tell that it's running by the fact that you now can't enter any more commands here, but that instead this command is stuck. It's stuck because we have a running web server. Now you can visit localhost 3000 and you should see hi there. And that's our first Dockerized application, even though, of course, at this point, we haven't written this Docker file ourselves and we don't fully understand what's happening there, but we're going to learn all of that throughout the next sections. To now stop this container, we can open up a new terminal by clicking on this plus here, and then you can run docker ps, which will list all running containers, and then grab this name of this container, which was started. It's an automatically assigned name, and run docker stop, and then this name. And this will now stop this container and shut it down. This can also take a couple of seconds, but thereafter this container is not running anymore, and therefore once this did stop, if you reload localhost 3000, you can't reach the site anymore. Also in that terminal where you ran docker run, you now are out of this running process again, and you can enter more commands. And that's it. That's this very first basic example, not too fancy and of course not a lot of work from our side, but it shows us that Docker was installed successfully, that it works, and that we kind of did create such a containerized application. Because we definitely did not install Node.js on our system, we did not run npm install in this project folder to install all third-party dependencies, and still we were able to bring up that web server and visit it on localhost 3000. And that was possible because of Docker. So now we know what Docker is, what containers are, why it's awesome, we set everything up, and we also got our hands dirty already. Now we definitely want to dive in deeper, and therefore I just want to let you know what to expect from this course and what will be inside of this course. We're pretty much done getting started and having this overview over what Docker and containers are, and therefore next we're going to dive into a block of sections which I call the foundation sections. So we're going to dive into a couple of sections which lay out a very important foundation which you need to work with Docker. We're going to dive into images and containers, and we're going to learn in detail what that is, how you can build your own images, how you can use existing images, how you can run and configure containers based on images, and how these two pieces work together. Thereafter, we're going to dive into data and a concept called volumes. You're going to learn how you can manage data in containers and how you can ensure that data persists so that it's not lost if a container is shut down and restarted and removed in between, for example. Thereafter, we're going to conclude the foundation block with a section on containers and networking. So you're going to learn how multiple containers can talk to each other, because you might be building an application where you have a Node REST API in one container and where you then, for example, have a React.js frontend in another container. And having these containers communicate with each other, that's something which matters and which you will learn in this module. Thereafter, we got a very solid foundation, which does not mean that we're done yet, but that you understand the core concepts. Hence, the next step is to dive into the real-life part of the course, as I like to call it. You could also say a bit more advanced concepts. We're going to have a closer look at multi-container projects and what could be tricky there and how to manage these projects. We're thereafter going to dive into a tool called Docker Compose, which makes managing containerized applications much easier, as you will see. I'm then going to explore utility containers, as I like to call them, together with you, and you're going to see what that is and why it might be interesting. And we're then also going to deploy containers and containerized applications. And we're going to do this with AWS as an example. Now, after this part, we'll be done with all the important Docker and container concepts and basics. Hence, the next step is to dive into the other big part of this course, Kubernetes. I haven't talked much about Kubernetes in this section because we first of all need to understand Docker and containers in detail before we can understand which problem Kubernetes solves. Well, by the point we reach this part, of course you will be in the position to understand it, and hence I will introduce you to Kubernetes, and we're going to dive into all the basics you gotta know about Kubernetes step by step. After having these basics, we are going to explore how we work with data and volumes in a Kubernetes world. We learned that earlier already at this point when we talked about data and volumes with just Docker. Now we're going to see how that translates to Kubernetes, and we'll have the same thing for networking and for deployment, because we will also learn how to deploy a Kubernetes cluster and how to deploy containers with Kubernetes instead of just standalone without Kubernetes. And that is the course. It's a huge course with plenty of examples and plenty of concepts. And therefore, let's continue and let me show you how you can get the most out of this course. Now, your success matters to me. I want to ensure that you get the most out of this course. And for that, there are a couple of things to keep in mind and to be aware of. Most importantly, of course, it's a video-on-demand course. You should watch the videos, but watch them at your own pace, at your own speed. Watch these video player controls, which you find in the video player, to speed me up if I'm going too slow, or to slow me down if I'm going too fast. Really make it your course and watch it at your pace. You can also pause a video from time to time or rewind if something isn't clear immediately. Docker can be a complex topic, and therefore it's perfectly normal that you might have to do something like that. In addition, I can recommend that you code along. We're not going to write that much code, to be honest, but we're going to write configuration files and we're going to run hundreds of containers. And I can only recommend that you follow along with these examples, that you write the same configuration files I do, and that you also try running these containers. If I'm going too fast, as I mentioned, pause the video to then code along and then unpause once you tried something out. Maybe sometimes even pause ahead of time and try something we're about to do together on your own first. This might be a great practice as well, and I can only encourage you to do that from time to time to ensure that you really get the most out of this course. In addition, of course, also make sure you repeat concepts from time to time. It's a huge course with a lot of sections, and after a couple of hours, it's easy to forget something which you learned earlier. So don't feel bad if you want to dive back into an earlier section or maybe in some lectures of that earlier section once you advance a bit more. This is something which can make sense to ensure that you really don't forget what we learned and that you can always apply all the key concepts when you need them. Of course, sometimes you also might be stuck, and we do have a Q&A section which you can also use to ask if you're facing any errors or anything like that. I also, however, recommend that you do use Google and Stack Overflow, because often you can get a quick answer there if something is unclear or if you're facing some error, and that might simply be faster than waiting for a response here. And you might also find other examples which help you understand a certain concept even better. Last but not least, as I mentioned, there is a Q&A section and you can always ask there if you're stuck, but I do encourage you that you don't just ask there, but that you also answer. Help your fellow students, because you will learn way more if you do that. If you help others, you are challenged to think about a certain problem and to solve it, and that is where you learn the most. So I can absolutely recommend that you do this as well. And if you keep all these things in mind and try using these different things throughout this course, you will get the most out of this course. And with that, let's now dive right into Docker and let's start digging a bit deeper into images and containers. So by now, we got Docker installed and we're all set to dive into Docker. And that's exactly what we're going to do in this module. This module is about the two core concepts, the two fundamental concepts you gotta know and you got to understand if you learn Docker and if you want to work with it. And that will be images and containers. Now, we already heard about containers in the first course module. In this course module, we will also learn about images, and we will explore how images are related to containers and how you need both to work with Docker. In this module, we will learn how we can use pre-built and custom images and what the difference will be. And most importantly, of course, we will learn how we can create, run, and manage Docker containers. So with that, let's dive right in. Let's understand what images and containers are and how we can work with these concepts to ultimately use Docker. So as mentioned, we don't just have containers, we also have images when working with Docker. Now, what is the difference and why do we need both? We already heard about containers in the first course module. You learned that containers, in the end, are small packages, you could say, that contain both your application, your website, your node server, whatever it is, and also, and that's important, the entire environment to run that application. So a container is this running unit of software. It is the thing which you run in the end. But when working with Docker, we also need this other concept called images, because images will be the templates, the blueprints for containers. It's actually the image which will contain the code and the required tools to execute the code. And it's the container that then runs and executes the code. And we have this split, this separation here, so that we can create an image with all these setup instructions and all our code once, but then we can use this image to create multiple containers based on that image. So that, for example, if we talk about a Node.js web server application, we can define it once, but run it multiple times on different machines and different servers. And the image is that shareable package with all the setup instructions and all the code. and the container will be the concrete running instance of such an image. So we run containers which are based on images. That is the core fundamental concept Docker is all about in the end. Images and containers, where images are the blueprints, the templates, which contain the code and the application, and containers are then the running application. And this will become clearer throughout this module once we start working with images and containers. And actually, let's start working with that right now. Let's see how we can work with images and containers when using Docker. I mentioned that containers are based on images. And actually, there will be two ways of creating or getting an image so that we then can run a container. The first way is that we use an already existing image. For example, because a colleague of ours already built it, or also very common, because we use one of the official pre-built images or one of the images shared by the community. And a great source for that would be Docker Hub, which you can simply Google to find hub.docker.com. And there you can log in, but you don't need to do this right now. Instead, here in the search bar, we can, for example, search for Node. And what we'll find is the official Node Docker image, which we could use to build a Node application container, a container which will later run a Node application. Now, this Node image, which we find on Docker Hub, can be used by anyone, and it is distributed and created and maintained by the official Node team. Now, we will use such official images a lot throughout this course and in general when working with Docker, but we can especially use it right away to get started with images and containers here. And all we need to do for that is open up the command prompt or terminal on your system, and then navigate in any folder of your choice and run docker run node. This command here will use this node image, which we find on Docker Hub, and it'll utilize it to create a so-called container based on this image. Because as I mentioned, containers are really just the running instances of images. Images contain the setup code, the environment. In this case, the node image contains the node installation. And then we can run the image to run the application, or in this case, to simply run the node interactive shell. Now, if you hit enter, this will give you an error that it doesn't find this image locally, which makes sense because it's on Docker Hub, and then it'll automatically pull it from Docker Hub. So now this downloads the latest node image from Docker Hub, and once it downloaded it locally onto our machine, it will run this image as a container. So let's wait for this download to finish here. And thereafter, you will see nothing special here. It's done and we can enter more commands. So did we now run the container? Did we now create a container based on an image? Well, yes, we did, but this container isn't really doing much. Node is, of course, just a software, you could say. And indeed, we can execute Node to get an interactive shell where we can insert command. But by default, and that's important, a container is isolated from the surrounding environment. And just because there might be some interactive shell running inside of a container does not mean that this shell is exposed to us as a user. Nonetheless, this container was created. And you can tell by running docker ps-a. PS stands for processes, and with the -a flag, this will show you all the processes, all the containers Docker created for us. And if you hit enter, you will see that a minute ago, I actually created a container And to make this a bit easier to read, I'll zoom out a bit and rerun this. And you'll see we created a container with this ID. The image was the node image. It was created 2 minutes ago. It exited, so it's not running anymore. And it also received a automatically generated name. We'll dive into names and into configuring containers in general in greater detail later. But what we see is that something happened, but that it's not running anymore because, as I said, a container runs in isolation. And even though we executed node as an image or as a container based on the node image, this alone doesn't do much because the interactive shell exposed by node is not automatically exposed by the container to us. That is something we can change though. If we repeat the command from before, docker run node, and we now add an extra flag in front of node, the -it flag, then we will actually tell Docker that we want to expose an interactive session from inside the container to our hosting machine. And hence, if we now hit enter, we actually are in that interactive node terminal where we can run basic node commands. For example, 1+1, but we could also use node APIs in here. But that's of course not the focus of this session. Now, the important thing about this here is that node here is now running inside of that created container, and it's just exposed to us by adding this extra flag so we can interact with that container and with node running in the container. Node is not running on our machine here. And I can prove this. Please note that here we're interacting with node 14.9, which is the version that at the moment I was recording this was pulled into this image and therefore is being used in this container. Now, if I quit this process with Ctrl+C pressed twice, now the container will shut down. When I quit this and I run node-v here like this on my system, so not inside of the container, I see 14.7 as a version. So locally on my system, I got a different version installed than the version we interacted with here, which proves that the version we did interact with must be the version from inside the container. And we don't need Node to be installed on our system at all in order to be able to run this Node container and interact with it. And that is really how you work with containers. At least these are some first steps of working with containers. And this also shows us what images and containers are. Images are used behind the scenes to hold all the logic and all the code a container needs. And then we create instances of an image with the run command. This creates then the concrete containers which are based on an image. And if we now run docker ps-a again, we see that we got two containers now. Both are not running anymore, they have been exited, but we have more than one container based on the same image. Both containers are based on the same image. And yes, they are not running anymore, but we could absolutely have two containers which are based on the same image up and running at the same point of time, simply by opening up multiple terminals and then, well, repeating this docker run command. This would absolutely be possible. And that's the idea behind images and containers. Images contain the code, the setup, the meat, you could say, and containers are then the running instances of those images. Now, in the vast majority of use cases, you don't just want to download and run an image that gives you an interactive shell, like the node image does at the moment. This is nice to get started and to have our first experience with containers and images, but it's not all we want to do. Instead, typically, you build up on those base images to then build your own images. Like, for example, here, we could build up on the node image to then execute certain Node.js code with that image. And of course, Node is just one example here. an example I will use a lot throughout the course, but the same would be true for PHP, for Go, for Python, whichever programming language you're using, whichever application you might be building. Typically, you would pull in the official base image and then add your code on top of that to execute your code with that image. And of course, you want to do all of that inside of a container. And that is a scenario where you need to build your own image, because your exact application with your code, of course, this does not exist on Docker Hub unless you shared it there. So therefore, now we'll build our own image, building up on this Node image though. And for that, I prepared a very simple Node.js dummy project, and you don't need to know Node to follow along. You can simply download this dummy project, you find it attached, and it contains 4 files here. A server.js file, which contains our main Node application code. In case you know Node, you can quickly see what this does. In case you don't know it, this starts a web server with Node.js listening on port 80, and we handle incoming requests to 2 URLs, to our domain /nothing, if it's a GET HTTP request, in which case this HTML code will be returned, and we handle post requests to store goal, where we then try to retrieve a goal key, a goal value from the incoming request body. We then log this goal to the console, and we set some user goal variable equal to that extracted goal. And then we redirect to the / route again, so to this route. And here we then render HTML code where we utilize this user goal variable, which has a default value, which is eventually overwritten to the entered goal value. And this variable is output here. This is JavaScript code executed with Node to bring up such a Node web server. But again, you don't need to know Node. This course is not about Node. This is just one example application which we want to Dockerize, which we want to run in a Docker container. Now, 2 other key things belong to this application. One key thing is the public folder, which has a CSS file for some styling. This file is automatically loaded in the end by telling the Node server to, well, just redirect requests to files to the public folder and then look for such files there, which is why a request to styles CSS will load style CSS, which is in the public folder. But then, probably the more important other key thing we have here is the package.json file. Here, we describe this Node application, and that is a Node exclusive concept. It has nothing to do with Docker, this package.json file. But here we tell Node which dependencies we have, which other third-party packages we need to run this Node application. In this case, that's the Express framework, which is a Node.js package we can use in our Node.js applications, and the body parser package. Now, if you would want to run this project locally without Docker, you would need to install Node.js from nodejs.org, for example, that latest version. And then thereafter, in your project folder, in a terminal opened in that folder, and here this is my default terminal, just integrated in Visual Studio Code, the IDE I'm using here, automatically navigated into this project folder. And in this terminal, you would need to run npm install. npm is another tool shipping together with Node.js, so being installed automatically when you install Node. And npm install will now download and install all the dependencies we need. And then thereafter, once you did this, you could execute the server.js file with the node command, and this would then start this server, and on localhost port 80, you could visit this application, set your goal, and see this in action. Now, this is the Node application running locally without Docker, and you don't need to install Node. This was just an example how we would run it without Docker. Now, of course, this course is about Docker though, so let's quit this with Control-C. Let's clear this console, and let's actually delete the Node modules folder, which was created after running npm install. And let's also delete the package-log JSON file here, so that we're back to the initial files. The git ignore file, by the way, is optional. It's just important if you're using git for version control. So this is now a Node application. How can we now build our own image that contains this application and that then also utilizes the Node Docker Hub image to run that code? To build this custom image, we need to go to the folder that contains our code, and in there we need to create a new file. A file named Docker file. This is a special name which will be identified by Docker. Now, to get the best possible support for writing such Docker files, I recommend that in Visual Studio Code, you go to the extensions area, and there you search for Docker, and you install this Docker extension, which I already have here. Make sure you install this Docker extension because this will help you with writing Docker code, Docker instructions. It's not a must-have, but it will make your life easier. And thereafter, you can go back to the Explorer view. So now we got this Docker file. And what do we put into this file now? This file will contain the instructions for Docker that we want to execute when we build our own image. So it contains the setup instructions for our own image. And typically here, you start with the from instruction, all caps from. This allows you to build your image up on another base image. And this is what you typically do. Theoretically, of course, you could build a Docker image from scratch, but you always want some kind of operating system layer in there, want some kind of other tool which your code needs. So therefore here, I want to build up on the Node image. And I can do this with from Node. Just entering the image name of an image which either exists on your system or under that name on Docker Hub. And this image now exists on Docker Hub, and actually, since we already executed a container based on this image, at the moment it also exists on our local machine, because when we ran a container based on this Docker Hub image for the first time, this image was downloaded and cached locally. So now this is basically both a local and a Docker Hub image. The most important thing is, though, that it will be recognized, that Node is a name Docker will be able to find, that there will be an image named Node. So now we're telling Docker, hey, in my own image, I want to start by pulling in that Node image. And then I want to continue. So that's now the first step. As a next step, we want to tell Docker which files that live here on our local machine should go into the image. And for that, we get the copy command. And here, a very simple instruction we could execute is copy dot dot. Now, what does this mean? You basically specify two paths here. The first path is the path outside of the container, outside of the image, where the files live that should be copied into the image. And if you just specify a dot here, that basically tells Docker that it's the same folder that contains the Docker file, excluding the Docker file though. So in this case, dot would tell Docker, this first dot would tell Docker that all the folders, subfolders, and files here in this project should be copied into the image. And now the second dot is the path inside of the image where those files should be stored. Every image, and therefore also every container created based on an image, has its own internal file system, which is totally detached from your file system on your machine. It's hidden away inside of the Docker container. And actually here, it is a good idea to not use the root folder, the root entry in your Docker container, but some subfolder, which is totally up to you. You can name it however you want. And here I will name this /app. Now all the files here in the same folder as the Docker file, and all the subfolders there as well, will be copied into an app folder inside of the container. And this folder will simply be created in the image and container if it doesn't exist yet. So that's one key step. Now, as a next step, we need to run npm install, right? Because that is what we had to do outside of the container as well. For Node applications, we had to run npm install in order to install all the dependencies of our Node application. And you also have an instruction for that, which you can give to Docker. You can tell it that after copying all the local files into the image, you want to run a command in the image. In this case, npm install. However, there is a gotcha here. By default, all those commands will be executed in the working directory of your Docker container and image. And by default, that working directory is the root folder in that container file system. Since I'm copying my code into the app folder here, I actually want to run npm install inside of that app folder as well. And a convenient way of telling Docker that all commands should be executed in that folder is that you set another instruction here before you copy everything, and that's the workdir instruction for setting the working directory of the Docker container and setting this to /app. And this tells Docker that all the subsequent commands will be executed from inside that folder, which makes sense because that is where we will have our code later. And now, as a side note, given the fact that we now did set the working directory to /app, we could also change copy to copy everything from the path the Docker file is in to just dot or /, which basically means to the current working directory inside of our Docker container. Since we changed that working directory to /app, not just run, but also copy will execute relative to this working directory. So now inside of the container internal file system, this relative path now points at /app. But we can also be more explicit here and set this to the absolute /app path like this. And I'm a fan of doing that since this makes it very clear where we're going to copy our files, and we don't have to guess or look into that file to see what the current working directory is. Of course, that is a simple file. It's easy to see what the workdir is, but if this would be a more complex file, it could be harder, and therefore I personally prefer setting this to /app here as well. Now with that, we have a lot of important setup instructions. The last instruction is that when all of that is done, we want to start our server. For that, we could add run node server, but this would actually be incorrect, node server.js. This would be incorrect because this would be executed whenever this image is being built. All these here are instructions to Docker for setting up the image. Now keep in mind, the image should be the template for the container. The image is not what you run in the end. You run a container based on an image. And therefore, with this command, we would try to start the server in the image, so in the template. But that's not what we want. We want to install all the dependencies there, yes. We want to have all the code in there, yes. But we only want to start a server if we start a container based on an image. Also, so that if we start multiple containers on one and the same image, we also start multiple node servers. So therefore here we have another instruction, and that's the CMD instruction, which stands for command. The difference to run is that this will now not be executed when the image is created, but when a container is started based on the image. And that's what we want. Then we want to run our node server. However, for CMD, the syntax is a bit differently. Here we want to pass an array, you could say, and then we have two strings in there where we split our command like this. So that's how we now tell Docker that whenever a container is created based on that image, we use the node command, which exists inside of that container, to run the server.js file. Now, if we would try to run it like this, we would not be able to see our application though, for one key reason. This node web server listens on port 80. And I mentioned and emphasized multiple times already that a Docker container is isolated. It's isolated from our local environment. And as a result, it also has its own internal network. And when we listen to port 80 in the node application inside of our container, the container does not expose that port to our local machine. So we won't be able to listen on that port just because something's listening inside of a container. Therefore, in the Docker file, after setting everything up, before specifying the command, which should always be the last instruction in your Docker file, we can add the expose instruction to let Docker know that when this container is started, we want to expose a certain port to our local system, so to our machine here, which will run this container. And then we'll be able to run the container such that we listen on this port. Now with that, we've finished our Docker file with all the setup instructions for a Docker image. Now let's see how we can utilize this custom image, build it, and how we can run it. So we got this Docker file. How can we now turn this into an image and then into a container ultimately? Well, we need to open up the terminal. And again here, I will simply use the terminal integrated into my IDE, which is the default system terminal though. And here, we can now run Docker, but not run, but build. Because now I don't want to run an image, at least not yet, but first of all, I want to create an image. I want to create an image based on the instructions in this Docker file. And that's what the build command does. It tells Docker to build a new custom image based on a Docker file. And here we now need to specify the path where Docker is able to find the Docker file. And if we just type a dot here, we tell Docker that the Docker file will be in the same folder as we're running this command in. And since I'm using the integrated terminal, this is already navigated into this project folder. Hence, the Docker file is in that folder. Hence, if I hit enter, this now creates this image. And you see it executes a couple of steps here. It executes the from command to take the node image, sets the working directory, copies our code, runs npm install. We can ignore the warnings here. Then exposes the port and recognizes this command, you could say. And at the end, it's done, and it built an image with this name here, with this ID. Now keep in mind, as mentioned in the first course module, on Windows the output looks a bit differently. Here you find your image ID here. You can also assign custom names to images, but for the moment we can go with that. So copy the ID that was generated, and then you can run docker run and use that ID here. And if you hit enter, this will now start this container, and you will see it doesn't finish, it keeps on running. And the reason for that is that the command we executed here starts a node server, which is also an ongoing process that doesn't finish. And therefore the container also keeps on running, because the command that was executed when the container is started is a command that doesn't finish. And hence the container keeps on going. But you will notice that if you visit localhost, you won't see the website, even though we exposed the port here in our Docker file. So why is that not working and what can we do here? Well, we are almost here. First of all, let's shut this container down because clearly it's not working as intended. To do that, you can open up a new terminal and there run Docker PS to see all the processes. And if you just run Docker PS without -a, you see only the running processes. And here we see one container based on this image we created. And it's still up and running here because, as I said, it doesn't quit automatically. Now we can stop this container manually by running docker stop and then using the container name, which was automatically assigned here. If I now hit enter, this takes a short while and it will shut down this container and therefore also the node server running inside of the container. Once this is finished, if you run docker ps again, you see no running container anymore. Instead, now you would have to enter ps-a to see your container there. It now exited. Okay, so now we shut this down. What went wrong though? Why were we not able to listen on port 80 for this custom container? Because one step is missing here. Yes, we have this expose 80 instruction in our Docker file, but actually this instruction only is added for documentation purposes. It doesn't really do anything. It is a best practice to add it, and you should add it to clearly document which ports will be exposed by your container, but you need to do more. You could actually also remove this expose 80 instruction and still do what I'm about to show you, and it would still work. So this instruction is really 100% optional, yet, as mentioned, recommended that you add it. But what really matters is that when you run the container with docker run, that you then add a special option. So therefore what we need to do is we need to run this container, but we need to add an extra flag here. And that's the -p flag in front of the image name, which stands for publish. And this allows us to tell Docker under which local port, so under which port on our machine here, this internal Docker container specific port should be accessible. And the syntax here is as follows. You have -p, and then you specify your local port under which you want to access this application. In this case, for example, 3000. This is up to you. And then colon, and then the internal Docker container exposed port. In this case, 80, since we're exposing 80 in this container. And with this now, if we hit enter, this again starts. But now if I reload localhost 3000, I see my application and I can learn Docker in depth. Because now this is published under the local port 3000. And this is now our first custom image based on the default node image with our own instructions and our own node app. And I'm pretty sure that at this point there still are many question marks in your mind and in your eyes, and I will get to all of them, but I hope this general idea here is clear. That we have a custom image based on an existing image, the node image, where we then have a couple of instructions, for example, to copy our code and install all dependencies. And then we create this image with the docker build command, and we then run a container based on that created image with the docker run command. And then here again, this container is still up and running. If we want to close it, if we want to stop it, we again have to first of all find the container name with docker ps here, and then we can run docker stop container name. And of course, there are also ways of assigning your own names and so on, and we'll get to these ways and these features as well. But for now, these are the basics you should be aware of. How to build your own image, how to run that image as a container, how to stop that container, and most importantly, you should understand how these core concepts work together. So we created our first Docker file. Therefore, we then also built our first custom image, and we ran the first container based on a custom image. Now there is way more which we can and will learn about this Docker file, and also about the Docker command and all the sub commands we can run there, all the different ways of configuring things. We are going to explore that. But before we explore anything related to that, it is important that we fully understand how an image and a container work and how they work together. And for that, let's say, in our Node application code, we want to change that code. We want to change that code and say my course goal with an exclamation mark here, for example. This is a tiny change made to this HTML code, which now should be reflected in our running application. So if I rerun this command to restart this container based on this image which we built, the application, the Node application, starts again. And if I now reload localhost 3000, I see this application again. But we also see one problem. My little change in code isn't reflected here. Keep in mind, I added an exclamation mark after my course goal. Here, we still see my course goal like this, without the exclamation mark. So why is this change not reflected? I mean, I even restarted the container in the meantime. In case you didn't do that, by the way, you learned that with Docker PS, you can see running containers. Then you can pick the name and run Docker stop to stop it, and then restart it. But again, that restarting didn't do anything here. I don't see that change in my web application. Because we have to understand how images work, keep in mind that this is part of our source code, our Node application code. What are we doing with that code? Well, in the Docker file, we instruct Docker to in the end copy everything inside of this project folder, including the server.js file, which holds my source code, into the container file system, to be precise, into the app folder. Then we run npm install, tell Docker that it should open up port 80, and start the server when the container is launched. Now, therefore, we do one important thing. We copy our source code into the image, and we basically take a snapshot of our source code at the point of time we copy it. If I thereafter edit my source code, as I did it here when I added this exclamation mark, this change is not part of the source code in the image. We need to rebuild our image to copy our updated source code into a new image. And that is really crucial. Now, if this sounds cumbersome and strange, that we have to rebuild our image every time we change our code, I have a good message for you. We will find a more elegant and faster way of picking up changes in our code later. But the core takeaway here is important and will always be true. Images are basically locked and finished once you build them. Everything in the images is read-only then, and you can't edit it from the outside by simply updating your code just because you copied that code in the past. The image doesn't care about the past. Once this copy operation is done, you can change your outside code however you want. You can even delete it, and the image will not be affected. You need to rebuild to pick up external changes and basically copy all the updated code into the image. So therefore, what we need to do here is we need to run docker build dot again to rebuild this image, and therefore to build a new image in the end. So let's wait for this operation to finish. And once we got this new image, we also got a new image name, because it now really is a totally new image. It's almost the same as the previous one, but technically it's totally different. It has totally different code inside of it. And we can now Docker run this new image by using this new image name. And if we do this now, and we reload localhost 3000, you now see the exclamation mark is there, and this change has now been picked up because we rebuilt a new image with our new code inside of it. And I'm putting so much emphasis on that because it is super crucial to understand that an image is really a closed template in the end. These instructions are executed to create an image, and thereafter it's locked, it's finished. And if you change something which you copied into your image thereafter, that has no impact. So with that, I'll also stop this newly created Docker container here. And we can now dive a bit deeper into images and again also containers, because there is more which we need to explore here. So an image is closed once we built it, once these instructions were executed. That's why we have to rebuild it if we need to update something in there. For example, when our code changed and we want to copy the new code into a new image. That's what we covered in the previous lecture. Building up on that, there is another important concept related to images which you also should be aware of. They are layer-based. Now, what do I mean by that? With that, I mean that when you build an image or when you rebuild it, only the instructions where something changed and all the instructions thereafter are re-evaluated. Keep in mind that I changed the code and then I rebuilt this image. We did this in the last lecture. Now, I did not change the code again since then. So if I now rebuild this image again by running docker build dot, you see this is super fast. It finished in like a quarter of a second. It was super fast because we see all these using cache messages here. Because Docker basically recognized that for all these instructions, the result when the instructions are executed again will be the same as before. We have the same working directory. The code I copy has not changed at all. There is no new file. No file has changed. And therefore, Docker is able to infer that it doesn't really need to go through that instruction again. Instead, whenever you build an image, Docker caches every instruction result. And when you then rebuild an image, it will use these cached results if there is no need to run an instruction again. And this is called a layer-based architecture. Every instruction represents a layer in your Docker file. And an image is simply built up from multiple layers based on these different instructions. In addition, an image is read-only, which means once an instruction has been executed and once the image is built, the image is locked in and code in there can't change unless you rebuild the image, which technically means you create a new image. That's what I covered before. But let's come back to these layers. An image is layer-based. Every instruction creates a layer, and these layers are cached. If you then run a container based on an image, that container basically adds a new extra layer on top of the image, which is that running application, that running code. Basically the result of executing the command which you specified in your Docker file. This adds the final layer, which only becomes active once you run an image as a layer. All the instructions before that final instruction are already part of the image, though, as separate layers. And when nothing changes, all these layers can be used from cache. Now, if I do change something in code, if I add more exclamation marks here or anything else, no matter what you change, if I now build this again by repeating docker build dot, you will see that now it takes longer because it only uses some results from cache. It used the work directory instruction result from the cache, but it noticed that for the copy instruction, it needs to run it again because it scans the files which it should copy in, and Docker detects that one file changed, and hence it copies in all files again. Now, here's the thing. Whenever one layer changes, I said that all other layers are also rebuilt. Docker is not able to tell whether npm install would now yield the same result as before. After all, we copied in our files again, and Docker does not do a deep analysis of which file changed where and if this could affect npm install. So whenever one layer changed, all subsequent layers are also re-executed, which is why here npm install ran again. So I hope this layer-based architecture makes sense and is clear. It exists to speed up the creation of images, since Docker only rebuilds and re-executes what needs to be re-executed. And that's of course a very useful mechanism. Now it also means that at the moment, whenever we change anything in our code, we also run npm install again, even though we as a developer know that this is unnecessary. Unless we changed something in package.json, which manages the dependencies of our project, there is no need to run npm install again, ever. Because if we just changed something in our source code, this has no impact on the dependencies this project needs, and therefore in Node's world, npm install does not need to be re-executed. And here we have our first tiny bit of optimization potential for this Docker file. Instead of copying everything like this and then running npm install, it would be better if we would copy this after npm install, but before we run npm install, we also copy the package.json file. And we copy that into the app folder. With that, we would pick up this package.json file, copy that into the app folder, then run npm install, and then copy over our other code. With this, we would ensure that this layer, the npm install layer, comes before we copy our source code. So in the future, whenever we change our source code, these layers in front of the copy source code command will not be invalidated, and npm install will not run again just because we copied in our source code again. So now only these layers would run again, and that will be more performant than running npm install again, which simply takes a certain amount of time to finish. I hope this makes sense. So if I now build this again, for the first time it will run npm install and copy in everything. But then here we got our image name. And if we now use that to run our container, and we reload, we see this change in source code, of course, which I made before. But if we now stop this container, first of all, with docker stop, and then go to server.js and update the source code again to remove all the exclamation marks again, you will notice that if I rebuild the image with docker build dot, it's now again super fast because it was able to use the cached result from npm install. Because the steps prior to npm install didn't change, because Docker sees that the package.json file did not change. It's the same as before, and therefore there was no need to copy that again and to run npm install again. The only change happened in this step, but that comes after npm install. So that's a first small optimization. But more important than that optimization is that you understand why we are doing it and that you understand this layer-based approach, this layer-based architecture. It's really important because it's a core concept in Docker and Docker images, and it exists for the reasons outlined in the last minutes. By now we explored the core concepts about images and containers. And I just want to provide a first summary on those concepts to ensure we're all on the same page. With Docker, it's all about our code in the end, our application we're building, for example, our web application. We put that code that makes up our application into a so-called image. And we don't just put our code in there, but also the environment, the tools we need to execute that code. You learned that you can create such an image by creating such a Docker file, where you provide detailed instructions on what should go into the image, which base image you might be using, which code and which dependencies should be copied in there, if maybe some setup step like npm install is required, and if you then want to open up some internal port so that you can listen to that from outside of the image and therefore ultimately outside of the container in the end. And that's of course important. Docker ultimately is about containers, not images. But images are an important building block. They are the template, the blueprint for your containers. You can then instantiate, run multiple containers based on an image. The image is the thing that contains your code and so on. The container, as you learned, is just an extra thin layer on top of the image, but still the container in the end is your running application based on an image, but then once it is running, standalone and independent from other containers that might be running. I want to emphasize though that a container does not copy over the code and the environment from the image into a new container, into a new file. That is not what's happening. A container will use the environment stored in an image and then just add this extra layer on top of it, this running node server process, for example, and allocate resources, memory, and so on to run that application, but it will not copy that code. So our code and the node environment is not getting copied 3 times here if we have one image and 2 containers. It exists only once in the image, and the containers then utilize that image and the code in it. This is how Docker manages this, and that's of course very efficient. And that's the core idea behind Docker, having those isolated environments that contain your app and everything that is required to run that app, all the environment, all the tools like Node.js, and having all of that inside of this isolated container. That's what Docker is about, and that's what we covered thus far over the last lectures. Now I want to take the time and have a look at how we can configure and manage our images and containers. Because thus far we saw how we can build an image and how we can run a container, how we can stop a container, but there is more we can do and more we should be aware of. And in general, one very important hint or note you should be aware of is that on any Docker command, you can add --help to see all available options. Now, there will be tons of options which you never or only rarely need, but you will see all available ways of running a certain command or of configuring a certain command by adding --help. That's an important hint. In the next lectures, we'll focus on a couple of core configuration options and core features built into Docker. We will learn how we can tag, which basically means name, images. We will learn how we can list the images we created in the past, how we can analyze and inspect images, and also how we can remove and clear images if we no longer need them. We will also have a closer look at containers and learn how we can name containers, how we can configure them in detail, how we can control them in detail, and we'll use --help for that to see various options there. We'll have another look at listing containers, running and stopped containers. We'll also see how we can restart containers that we stopped in the past. And we will also learn how we can remove containers after they have been stopped when we don't need them anymore. So that's a broad variety of things we can do with images and containers. Let's dive in. Now I'm back in the demo project we worked on before, and I'll bring up that built-in terminal again. But you can, of course, also open up a default terminal outside of Visual Studio Code. And there we got various commands which we can run with help of the Docker command. And as I mentioned, if you, for example, run docker -- help, you get a list of the built-in main commands you can run with Docker. And you see, there are quite a lot of commands there. Well, good news is a lot of these commands will not really matter to you in the vast majority of cases. There also are some commands from the past where we nowadays have better ways of achieving something. But still, you see, we have quite a lot of commands here. You can obviously read these descriptions to see what these commands do, but it will come down to a couple of core commands you should be aware of. In addition, there also are some commands which also could be replaced by other commands executed differently. In general, with Docker, for some operations, you have multiple ways of performing that operation. Now, I want to start with managing images and containers, since that is what Docker is all about. And we already saw, for example, that you can list all containers by running docker ps. And this shows you all running containers by default. Now, if you add -a, you see all containers you had in the past, including the stopped containers, which are not running anymore. As a side note, if you run docker ps -- help, you see all available config options for docker ps. And here's the -a flag, which we used to show all containers. So, docker psa shows us all containers, including the containers we stopped. And one important thing you can also do with Docker is you can restart a stopped container. You don't always need to docker run a new container, because that's important. With docker run, you create a new container based on an image, and that new container is started thereafter. Sometimes that is what you want, but sometimes it's not. If nothing changed about our application, about the dependencies and our source code, and our image didn't change, there is no need to create a brand new container. We can just restart an existing container. And for that, we can just search for stopped containers with docker psa. Now, you might see a different output than I do here, because I'm also working with these containers off screen, deleting some, which we'll learn later, and adding new ones. But here you see my history of Docker containers I worked with recently. And if nothing changed about our code and about our Docker file, we can just grab, let's say, this one, the most recent one which exited, and restart that with docker start. If we run docker start and then the container ID or name, this will bring the container back up. Now you see, it starts the container in a different mode. It's not blocking the terminal as it did with docker run, but I can tell you this container is up and running. And you can verify by running docker ps without the -a flag to only see the running containers, and you should see this container here. And we can also visit localhost 3000 and reload there, and there our application is up and running, thanks to this restarted container. But again, as I mentioned, this restarted container is in this strange mode where, yes, it did start, but no, we're not really able to interact with it or to see the logs. Instead, it started this container and then returned to the terminal so that we could enter more commands. And as I mentioned, that's different to what docker run did. Well, that's something we're going to explore next. Now, there is more we can do with the docker command than with containers and images. We already saw a couple of different commands in action, and I want to come back to this mode which we have here when we restarted a container, and the mode which we had when we initially started a container. Here, when we're restarting it, the process in our terminal here finished immediately. We're not attached to this running Docker container in the terminal anymore. Nonetheless, it clearly is still running, as we can see with docker ps. So this container is running, it's just not blocking us here in the terminal. And that's different compared to the docker run command we executed before. If I run this again, binding to a different local port, since 3000 is already used by the already running container, but if I use a different port here, I'm starting a new additional container based on the same image. So therefore, with Docker PS in a different terminal here, we see we got 2 containers up and running now. But you see that for Docker run, we're stuck in this process. I can't enter more commands here. I mean, I can type, but I can't commit them. I can't confirm them with enter. Instead, this process is blocking this terminal. And with Docker start, that was not the case. Now, this is not a bug or anything you have to accept. This is something you can configure if you want to be in this attached mode or in detached mode. And it's just the case that for starting with Docker start, the detached mode is the default. For running with Docker run, the attached mode is the default. And now the question, of course, is which mode do you want and why does this even matter? Well, in this example application, I am logging something to the console whenever we set a new goal. So here, if I add learn Docker in death as a goal on localhost 3000, that's my started container, which was detached, we see nothing in the console anywhere. On the other hand, if I go to localhost 8000, which is that new container we ran with Docker run, and I set my goal here, you will see that it also shows up in the terminal here, because here we're attached to this running container. And attached simply means that we're listening to the output of that container, for example, to what's being printed to the console. And this might or might not be what we want. We can also run a container in detached mode if we want to. We don't have to accept that default of being attached. For this, I'll quickly stop this more recent container which I started with Docker stop, which will take a couple of seconds. So that's the container we started with Docker run. And once this is stopped, I will rerun it, but now in detached mode by adding -d as an extra flag in front of the image ID here. If I now hit enter, you see now I just get the ID, the automatically generated ID of the new container. You see with Docker PS that we have this container up and running. That's the shortened ID of that up and running container, by the way. And we see that container is running, and therefore visiting localhost 8000 also works. But now if I learn Docker in death, for example, here on localhost 8000, we don't see that log in the terminal where we executed Docker run, because now we're not attached to the output since we used the -d flag to start in detached mode. The advantage is that we now can use one and the same terminal to also do other things. If you still want to look into your running container, you got 2 ways of doing that. For one, we can see with Docker help that there is an attach command. So we can attach ourselves again to a running container. We can simply find the container and use its name or its ID, both works, and then run Docker attach and that name, and we are attached again. And therefore now if we change it again and set a new goal, we do see this output again. So that's one way of doing it. But actually, let me stop this container again. And let me restart it thereafter. Now in detached mode automatically, since that is the default for Docker start. And let me show you another way of getting access to, for example, the log messages that are printed inside of a container. This is running again. If I now type learn Docker in death here and commit this, so I save this and set this goal, We don't see the goal because we are detached, and we could attach again to see future log messages. Or another thing we can do, another useful command, is the docker logs command, which fetches the logs that were printed by a container. And here we can first of all find the container. Eloquent Brown is the name of the container I'm interested here. And then we can run docker logs on that container, and we see the past logs that were printed by that container. We can also, if we inspect the options of docker logs, enter follow mode by adding -f to keep on listening. So basically we're now attaching ourselves again. So if I add -f here, we again get this attach process where we see future logs, future output by that container again. So these are the different options we have for that. And I'm spending a lot of time on that because it is important that you understand the difference between a running and a stopped container and an attached and a detached container. No matter if it's attached or detached, it's still up and running. But if you then need information from inside the container, you can use Docker logs or attach yourself to the container again to get that extra information. Now with that, I will again Docker stop Eloquent Brown to bring down that container and detach myself again here. Now one last note about all of that. If you would want to restart a stopped container like Eloquent Brown here in attached mode right from the start, you can do so by adding the -a flag to the start command. Now you start this in attached mode. So now I hope you liked this video, you enjoyed the tutorial, and you have a first good understanding of what Docker is and how you can use it to build images and run containers. If you want to learn way more about Docker and how to work with data there, persist data in containers, and synchronize data with data on your host machine. If you want to learn how to connect multiple containers, how to set up a container network. If you want to learn how you can leverage Kubernetes to deploy containers in a scalable and production-ready way. If that's all something which sounds interesting to you, you also might want to check out my complete Docker and Kubernetes guide. Of course, you find a link below the video with a nice discount, and I would love to welcome you on board there. So hopefully see you there. Otherwise, hopefully I see you in another video.